In physics, there is an ancient practice that was more fully developed in the German universities of the 19th and earliest 20th centuries. Coined the Kadunkan, or thought experiment, by the physicist Hans Christian Ørsted, it is a way of considering what a theory might say about a specific physical situation before trying to determine whether that experiment could actually be done. The purpose of the thought experiment is to see if the theory, when applied to the situation, will yield a reasonable description of the behavior of the system, and in practice, they are often developed and used to refine and refute various hypothetical or theoretical descriptions of a physical system. According to L.B. Yeats, a thought experiment is a device in which one performs an intentional, structured process of intellectual deliberation in order to speculate within a specifiable problem domain about the potential consequence for a designated antecedent. As such, the ability to develop these is a powerful tool in a scientist's repertoire, used to dig down into the subtle implications of a theory's framework and philosophical assumptions in order to more fully understand what the consequences of the theory will be. Sometimes they're used to prove the logical consistency of a hypothesis, while at other times they will be put forward to disprove some explanation of physical behavior. Perhaps the most famous Kadunkan experiment involves a cat in a box, a radioactive source along with some detection instrumentation, and a vial of poison gas. The man for whom the cat is named, Erwin Schrodinger, proposed the idea as a way of putting on display what he considered the underlying absurdity of the Copenhagen interpretation of quantum mechanics. He objected to the claim that the world of the very small is governed by statistical processes that are only resolved once an observation is made of a system. However, rather than refute the point of view of the group centered around Niels Bohr, Schrödinger's cat in a box illuminated the utter strangeness of quantum phenomena and initiated a train of experimentation that would help physicists define how the bizarre behavior of the world of subatomic and elementary particles becomes what we see in our everyday experience. To understand this debate and its philosophical implications, we need to take a look into the life and work of the brilliant and passionate man who flouted convention personally while helping create a revolution that he came to see as wrong and misguided. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 2, A History of the Atom. Episode 25.1, Supplemental. Erwin Schrodinger and the world's most famous cat. Over the course of the next few episodes of the podcast, I'd like to write a bit of an epilogue to our narrative on the history of the idea of the atom. In the course of creating this narrative, I had to make a number of decisions as to what to include and what to leave aside in the interest of crafting something that flowed smoothly and made sense. This is probably a process I expect every historian or writer must do, and it is what makes it so useful to read history from different sources and different points of view. In our case, one of the things I mostly set aside was a discussion of many of the philosophical implications of the scientific models as they were being developed in order to focus on the science, how it was done, and how certain conclusions were drawn from the observations being made. This was especially true for the quantum mechanical models where, aside from the discussion of the Copenhagen interpretation, we just sort of accepted the philosophical assumptions of the various models and mathematical frameworks because of their ability to explain the various data and make accurate predictions of the outcomes of new experiments. What I'd like to do over the course of 3 or 4 episodes is remedy that exclusion. In the course of our story, There were a number of historical concerns of a philosophical nature about what an atomic model meant and what a scientific hypothesis actually represents. As quantum models began to produce deeply counterintuitive descriptions of the nature of matter and how it behaves, there were additional questions about what it meant to make observations and whether the assumptions of Newtonian determinism were valid. Moreover, as the systems being studied became increasingly hard to make sensory-based observations of, questions arose as to the reality of the explanations being presented as existing. Such questions fall into the broad philosophical fields of metaphysics and ontology, as well as in the area of epistemology, that is, the study of the nature of knowledge. Now, as a side note, I think it's telling that many of the scientists most deeply engaged in this work, both then and now, have strong backgrounds in philosophy. Men such as Bohr, Pauli, Heisenberg, Einstein, and Schrodinger all studied philosophy in a structured and incisive way, even if they did not do so formally in many cases. As such, their investigations into the nature of matter were deeply infused with philosophical speculation and implication. Others, such as the aforementioned Hans Oersted, Austrian physicist Ernst Mach, and German chemist Wilhelm Oswald, made strong assertions about the nature of scientific knowledge that would profoundly influence the direction of the theoretical research of the early 20th century and how it would proceed. As part of this discussion, I'd also like to talk bibliographically about a few of the individuals involved in these investigations that I've only mentioned in passing so far. It is usually the case that a person's philosophical views grow out of their worldview, which is, in turn, deeply influenced by the life they live. In the case of our first topic and subject, it is unquestionably true that the world in which Erwin Schrodinger grew up and interacted profoundly influenced the way he thought about the philosophical issues raised by the scientific work that he became involved in. Erwin Schrodinger was born into a well-off, even bourgeois, Austrian family in Vienna in August of 1887. As an only child, raised by a number of women, Schrodinger was every bit the product of the decaying but culturally glorious Austro-Hungarian Empire of its time. Like so many of the other contributors to the quantum revolutions of the 20th century, he was born into a family with several generations of academically trained scientists or industrialists. Raised by a mother, an aunt, and a nanny, his early childhood was marked by tutors, theater performances, and a life made easy by the comforts of living in one of Europe's most cultured cities. Schrodinger was multilingual from the time he could begin speaking and could read almost from the time he could talk. The Vienna he was raised in boasted the finest musical tradition in all of Europe, one of its most prestigious universities, and was the capital of one of the last great autocratic empires. It was also deeply stratified, filled with ethnic tensions, and rife with anti-Semitic attitudes. Erwin first attended formal education when he was 10, and throughout the next 8 years, he excelled, consistently placing at the top of his class and uniformly impressing his instructors at every level with his brilliance. By the time he graduated from gymnasium, he could speak German, English, French, and Spanish well enough that later in life he would frequently answer questions during his seminars in the asker's native language. In 1906, Schrodinger would enter the University of Vienna as a student in physics. While the university at times had been a center of cutting-edge research in physics, boasting among its faculty the likes of Joseph Stephan, Ludwig Boltzmann, and Ernst Mach, in 1906 its Department of Physics was reeling. Just a year earlier, the department's most illustrious researcher, Ludwig Boltzmann, had succumbed to the bipolar disorder that afflicted him through most of his life, and he committed suicide. By 1906, a replacement had not been found, and so Schrodinger ended up spinning his wheels for about a year, until the young and energetic Franz Hasenhüttl was hired. Hasenhüttl was a brilliant physicist who had studied under Boltzmann and had come within a hair's breadth in 1904 of deriving the mass-energy relationship in what would become Einstein's special theory of relativity. He was also a gifted teacher whose lectures captured Schrodinger's attention and curiosity. Perhaps more importantly, Hasenroll was completely up to date on the most current physics being done in Europe, knowledge that he passed on to his students in Vienna. It was during this time that Schrodinger embarked on the first of what would be many romantic affairs during his life. While this is certainly a scientific biography, and thus the intention is generally to stay away from the more personal details of our subject's life, it turns out that Schrodinger's scientific creativity was closely tied to his romantic liaisons, of which there were many throughout his life. While it is certainly not my intention to dwell on this aspect of his life any more than necessary, it should be understood that in Vienna at this time, as would be the case in Berlin from about mid-1920s to the mid-1930s, the cultural norms were vastly different than those we tend to be more familiar with from Victorian England. Among the richer elite, there was a certain flexibility of romantic attention, with little stigma attached to those activities many would find objectionable when coming from the strictures of Victorian morality. After a typical course of study, Schrodinger would complete his PhD in 1910, and as required by the law of the land, would enroll to perform his obligatory military service. Trained as an artillery officer, as befitted his social class in the empire, below the cavalry with the aristocrats, but above the infantry of the average resident, Erwin took care of his responsibilities with little trouble and returned to take up the assistant role at the university. As part of this position, granted in 1912, Schrodinger was required to do additional original research to move up to the next level of the professorial ladder. While more theoretically inclined, he would do experimental work in magnetism, beginning a trend of being able to work in a broad number of problems in many different subdisciplines of physics. Over the next 2 years, Schrodinger would continue his experimental researches, as well as, after another failed love affair, publish his first truly important piece of theoretical work. Beginning with Boltzmann's statistical description of matter from kinetic theory, Erwin provided an improved description of the interaction of atoms within molecules. Had it not been for the outbreak of the Great War, in part due to events that took place there in the Austro-Hungarian Empire in which Schrodinger was living, he would have likely continued on this path up through the Austrian academic ranks. However, the war was to call him away into military service and, eventually, destroy the empire and he and so many others had taken for granted. In his time as an artillery officer and battery commander, Schrodinger would see limited direct combat duty on the Italian front. Even so, during those few engagements he did take part in, Schrodinger did well enough that he was awarded a military citation for serving with distinction during combat. During downtime between battles or at postings further from combat, he did theoretical work, mostly in gases and fluids. In 1916, he was recalled to Vienna to teach classes in meteorology to anti-aircraft gunners, thus avoiding the worst of the latter part of the war. It is during this time that he seems to have really immersed himself in relativity theory, shortly after the publication of the general theory, and quantum theory, writing a number of less important papers on both topics that showed his increasing mastery of the ideas found in both frameworks. It is also during this time, however, that things went from not very good in the Austro-Hungarian Empire to very bad. As the Entente powers' blockade really began to take hold, food shortages became common, which of course led to unrest within the capital. Even after the war ended, the blockade continued, causing untold suffering until Herbert Hoover, head of the American Relief Agency at the time, personally visited the scene in 1919 and arranged for large quantities of American aid to be sent to the region. It is during this time that it is thought that Schrodinger first contracted a mild case of tuberculosis, something from which he would suffer off and on for the rest of his life. It was during this time of great turmoil that Schrodinger, like so many before him had done, turned to philosophy as a way to cope with what he was experiencing. He found himself reading first Wittgenstein and then Schopenhauer. From this, he was introduced to Eastern philosophy, specifically the Hindu Vedanta, something that would influence his thinking deeply over the course of the rest of his life. The next 2 years was a nearly continuous litany of hardship and tragedy, as his father died during the first round of hyperinflation that swept Central Europe, and it wiped out the last of the family savings. Schrodinger's university salary was such that he could never hope to support a family, and thus his marriage prospects were extremely limited. Because of this, when the first good university professorship was offered to him in Jena, Germany, he took it. This allowed him to marry and began a series of moves over the course of the next few years. During his time in Jena, Erwin wrote a paper on quantum theory of light through an experimental analysis that was broadly equivalent to the classic double-slit experiment performed by Young. The results confirmed the wave theory approach, thus reinforcing Schrodinger's sort of inherent belief in all the types of descriptions of physical behavior provided by classical physics. This deeply inherent bias, something Schrodinger probably developed as a result of growing up in the very conservative Austro-Hungarian Empire, would influence his work going forward for the rest of his life. Also during this time, he wrote what would become the definitive encyclopedic article on color theory, a work that would be referenced for many, many years to come and would, beyond all of the other work that he'd done, really establish his scientific reputation throughout Central Europe. Over the next few years, he took positions in Stuttgart, Breslau, and finally Zurich in Switzerland. This post was a fairly prestigious one that was offered on the basis of his broad research interests rather than based on any particular brilliant piece of work that he had done. At this point in his career, Schrodinger was thought of as a solid, respectable physicist who could teach any subject in the curriculum with clarity and energy, as well as advise students in their research. In no sense at this time was it thought that he would be able to offer truly revolutionary work or insights in the field of physics. Schrodinger's start in Zurich was not very auspicious. Shortly after his arrival in 1921, the tuberculosis he had contracted in Vienna at the end of the Great War flared up, and he was forced to take an extended period of convalescence. At the time, it was thought that dry mountain air would stimulate the formation of red blood cells to fight the disease, though it is more likely that the oxygen-poor environment found at high elevations starved the tuberculosis bacteria of resources needed to multiply, thus allowing the body time to fight those bacteria. As such, Schrodinger would return several times during his 6 years in Zurich to a mountain resort near Davos known as Arosa. On several of these trips, he would be accompanied by various mistresses. For some reason, the combination of the energy of a new romance and the tension it created, and the ability to do scientific work away from the distractions of everyday life, would lead to the best work during his career. The first instance of this was in 1922, when he developed a paper that discussed electron orbits. In the paper, he noted that the electron would return to its original place in an orbit after a whole number multiple of a certain physical quantity had been traveled. This would prefigure the work of Louis de Broglie. The other insight that he made during this time was that the solution developed to this equation would have two results, one containing only real numbers and the other having imaginary numbers. This meant that the best physical description of the solutions would be to think of them as having the properties of waves. Near the end of that year, Schrodinger's physical health recovered sufficiently that he was able to resume his lecturing duties. In his inaugural lecture, he discussed the possibility that certain physical conservation laws might be violated on an individual interaction level, and thus only hold to be true statistically, i.e., when averaged out over many interactions. This was a profound claim, one that he would walk back sometime later in his career after the controversy over the Copenhagen interpretation. For the next several years, he would produce nothing of real import until 1926, when he would burst forth with the 6 papers that would define his legacy. first outlined in a rosa, again while consorting with an unknown mistress, these papers would put forward his theory of wave mechanics, something we discussed back in the episodes on the mathematical atom. I would refer listeners to these episodes if they're interested in knowing more about this description of the electron's interaction with the nucleus of the hydrogen atom. This, of course, led to that controversy with the Copenhagen group and Heisenberg specifically over matrix mechanics and how to understand the nature of the electron in an atom. At the 1927 Solvay Conference, the battle shaped up with Bohr, Heisenberg, Pauli, and Born on one side and Einstein and Schrodinger on the other. As discussed, Bohr carried the day, and it was the Copenhagen interpretation that was adopted by the majority of the physicists who adopted any philosophical framework at all. Around this time, Schrodinger was offered the professorship in Berlin, recently vacated by the retiring Max Planck, on the basis of his work in developing wave mechanics. This brought him into regular contact with Einstein, who had a non-teaching position there, something that led to the development of a lifelong friendship and collaboration. Shortly after Schrodinger had published wave mechanics, there arose a debate as to what the wave actually was a wave of or in. While he preferred to think of it as some sort of a wave in the physical variables of the electron's position and momentum, there were two other ideas put forward. De Broglie put forward an explanation known as a pilot wave. In this description, the wave was a sort of thing that carried the particle-like electron along a path around the nucleus of an atom, a bit like a surfer on a water wave is carried across the surface of the ocean by the action of the wave. The other interpretation was given by Max Born, who showed that the square of the wave function would give the probability of finding the electron at a particular location. Thus, he put forward that the wave function was an expression of the state of the system that incorporated everything that can be known about a system before an observation is made. When an observation is made, though, the interaction of the system with the measurement device is said to collapse the wave function from a set of probabilities into a specific outcome, or eigenstate, as it was known. It is this interpretation that was incorporated into the Copenhagen picture, along with Heisenberg's uncertainty principle and Bohr's complementarity principle. Both Einstein and Schrodinger found this description of quantum systems unacceptable for a variety of reasons. We'll leave Einstein's objections until our next episode. Following the Solvay conference, Schrodinger settled into his position in Berlin, and for the next 5 years, he would live the life of a respected European professor, even if a bit more informally than his peers were accustomed to. Contrary to the usual custom of lecturing in a dark suit and tie, Schrodinger would wear jaunty bow ties and sweaters in the winter and open-collared, short-sleeved shirts in the summer. It was not uncommon for him to arrive at conferences dressed as an alpine hiker or weekend tourist. It is likely that he would have remained at this post until his retirement had Hitler not come to power in 1933. With the expulsion of Jewish academics in that year, Schrodinger rejected the new state of affairs and found a way to immigrate to England with an offer from Oxford, where he would stay for the next 3 years as an itinerant researcher and lecturer. It was after moving to Oxford that Schrodinger developed the experiment for which he is best known. To best understand the context of the idea, we need to understand why we felt it was necessary to develop it. As I mentioned, both he and Einstein found the probabilistic principle of Born deeply troubling and counterintuitive. Schrodinger strongly believed that classical systems should behave and be described classically rather than according to the principles laid out by Bohr and Heisenberg. In a series of letters and conversations with Einstein, who was now ensconced at Princeton, Schrodinger explored a series of macroscopic applications of the Copenhagen interpretation until he hit on the one that is best known, the Schrodinger's cat Kadunkan experiment. In case you've never heard it expressed in the form Schrodinger put it forward, let's take a moment to go over it. Taken from Schrodinger's original paper is the following description. Let's say we have a cat confined to some sort of steel box. Also in the box, but free of interference from the cat, is a Geiger counter along with a very small amount of radioactive material. In the course of 1 hour, the radioactive sample has an equal chance to decay or not decay. If the decay takes place, it will be detected by the counter, which will trigger a mechanism that will release a hammer, which will smash a small vial of hydrocyanic acid. When this acid reacts with the air in the box, it will release a cloud of gas that will kill the cat. Now, the Copenhagen interpretation says that the wave function of the atomic sample will remain as what is known as a superposition of both outcomes, one of having decayed and one of not having decayed, until some observation is made which will collapse the wave function into one of its two possible eigenstates. Due to the causal chain within the box, this superposition of states will extend to the cat, which will exist in both an alive state and a dead state until the lid is taken off the steel box, an observation is made, and the superposition of states is collapsed into a single final outcome. Hence, a description of microscopic matter is now rendered up to a macroscopic situation with seemingly absurd results. What should be understood is that Schrodinger says that nowhere in the equations does one actually find this collapsing the wave function business that the Copenhagen interpretation purports. Rather, he claimed, it was made as an ad hoc assertion by Bohr and Born, and it had no basis in reality. So how does one answer this thought experiment from the perspective of the Copenhagen interpretation? Well, kind of before you do that, you can actually say, well, maybe Schrodinger's right, at least in part. There is no mathematical description of a collapsing or resolving wave function in the theory, and as such, positing this sort of mechanism based on probabilities is incorrect. However, this point of view only nullifies that part of the Copenhagen interpretation and not the rest of it. The description of the wave function as being related to the probabilities of finding the electron in a certain position still holds, as Born's interpretation of the Schrodinger wave function as being related to that probability is still found in the mathematics of Schrodinger's wave mechanics. Another response is to suggest that no matter how unpleasant or counterintuitive the Copenhagen interpretation might be, it does in fact describe the behavior of things in nature. A number of recent experiments have recorded subatomic systems such as photons and beryllium ions as existing in multiple superimposed states simultaneously, just as the cat would do in the thought experiment. Additionally, tests done with systems comprised of larger collections of particles also display this behavior. It should be emphasized, however, that nothing even close as being as large or complicated as a cat or any living thing has been placed in such a situation. The closest thing proposed to date involves a flu virus, and that experiment has yet to be done. It should be noted here that there is a logical flaw in the experiment that goes back to certain assumptions made from Schrodinger's philosophical background. Schrodinger, like most of those who were trained scientifically at the University of Vienna, was influenced by the philosophical views of Ernst Mach. While we will discuss these views in much more detail in a later podcast, Mach is considered to be the founder of a view of scientific inquiry known as positivism. As part of this epistemological system, or sort of a theory of knowledge, Mach claimed that science had to be based on what one could observe with one's actual senses. Hence, Schrodinger's thought experiment says that the wave function won't be collapsed until the lid is physically removed and the state of the cat is physically observed using human senses. However, if one extends the idea of observation to any active detection, it is clear that the Geiger counter's detection of the atomic decay is sufficient to collapse the wave function without the need for an actual determination of the state using senses. Known as objective collapse theory, this idea would support the claim that no superposition for the cat actually exists. A response that gained popularity in the late 1950s due to the work of Hugh Everett and Roger Penrose is what is known as the many worlds hypothesis. This view is that the wave function is never actually collapsed. Rather, at the point the observation is made, If there are two possible outcomes, then there become two possible realities, or I should say, two actual realities. In this case, there would be a reality in which the cat is dead, and another in which the cat is alive. At the branch point, as it is called, there are two realities created that, once established by observation, cannot interact with each other. This interpretation of the superposition of states idea in quantum theory has, of course, captured the popular imagination and is the basis of the plot of many a narrative in popular media, such as Lost and the new Star Trek movies. As can be seen with Schrodinger's thought experiment, it is a clear demonstration of the strangeness of the behavior of quantum systems, and it has engaged the interests of scientists and philosophers alike for the last 80 years. Its ability to focus inquiry into specific activities designed to answer the questions raised has guided physics and philosophy alike. It should be noted, however, that many physicists have ignored the issue of interpretation of the mathematics, either saying, as Dirac did, that no interpretation is possible due to the fundamental incompatibility of quantum behavior and our classically based perceptions, or that the interpretation doesn't really matter in making progress on solving problems of a quantum nature, and so we should, in the words of David Mermin, shut up and calculate. In either case, the proponents would say that the quantum theory is to be found in the mathematical description and that nothing else at all is very important. The cat, in a sense, marks the end of Schrodinger's productive work in physics. Unhappy in Oxford, Erwin would make the terrible decision to return to Austria and take a position in Graz in 1936. This would involve him in the events of the Anschluss, and he would flee first to Italy and then to Ireland, where the Institute of Advanced Physics at Trinity College in Dublin would offer him a position, and he would stay for the next 17 years. While there, he would spend much of his time attempting, in conjunction with Einstein, to create a grand unified theory that would combine gravity with the other interactions being studied. Of course, as we know, those efforts were significantly unsuccessful. In 1944, however, Schrodinger would publish a work titled, What is Life? This work, based on a series of lectures he had given in 1943, explored the idea that a complex organic molecule could encode genetic information in the covalent bonds that made it up. This encoding of information, known as a gene, was first suggested in the work of Max Delbruck and H.J. Mueller in the 1920s, but Schrodinger's book took to deriving the results from first principles. This work is credited for stimulating efforts in the 1950s to discover the carrier of genetic information, not yet known to be DNA, as well as the resulting structure of the molecule. Both James Watson and Francis Crick would cite Schrodinger's book as a source of inspiration for their early work that would eventually unravel that particular puzzle. In 1956, the great physicist would finally return to his home country when he was offered and accepted the chair of physics at the University of Vienna. On the 4th of January 1961, at the age of 73, he would die of the tuberculosis he had carried with him from the last days of the Great War. In his life, this man of immense, passionate energy would recast the way we understand the nature of matter. One of the last products of the great pre-war empires and a reluctant carrier of the banner of quantum physics, Schrodinger would leave as his legacy a piece of thinking that continues to challenge and resonate 55 years after his passing. In our next episode, we'll take up what is one of the greatest running debates in the history of scientific conversation, that of Bohr and Einstein over the nature of the Copenhagen interpretation that began at the Solvay Conference and continued for years afterwards. Between now and then, if you're enjoying the podcast, why don't you go out and leave us a review on iTunes, as that'll really help us spread the word about the work that we're doing here and the information that we're trying to spread. Also, feel free to invite some of your friends to join the crew. We're here in port, we're telling stories, and it'd be a great time to have folks come aboard. So until next time, full sails on your journey.